Space. It's where things happen. Time. It's when things happen. We can measure where things are and when things take place. But in modern physics, we realize when and where are actually part of the same question. Because when it comes to understanding the universe, we need to replace three-dimensional space plus time with a single concept, four-dimensional space-time. Hi, I'm Jangid and this video is part of my Science GD assignment. In this video, we'll explore and learn space-time concept with the help of animations. Consider a cartoon character, Andrew. Let's assume Andrew goes in a straight line from one point to other. To understand motion and movement of Andrew from one point to other, we'll need to make our cartoon physics look like physics. We'll need more panels. More panels, please. Okay, in each panel, Andrew's in a slightly different place, so I can see each one records where Andrew is at a different time. But it would be easier to see what's going on if we could cut out all the hundreds of panels and stack them up like a flipbook. Right. Now let's flip through the book so that we can see one panel after another, getting through 24 in every second. Now you can see Andrew is walking along. Drawing all those panels and putting them into a flipbook is just one way of recording the way Andrew is moving. It's how animation or even movies work. As it turns out, at Andrew's walking speed, it takes 2 seconds to get past each fence post, and they're spaced 4 meters apart. So we can calculate Andrew's velocity, how fast he is moving through space, is 2 meters per second. But we could work that out from the panels without flipping through them. From the edge of the flipbook, we can see all the copies of the fence post and all the copies of Andrew. And he's in a slightly different place in each one. Now we can predict everything that will happen to Andrew when we flip through 24 pages every second, including his speed of motion and just by looking. No need to flip through at all. The edge of this flipbook is known as a space-time diagram of Andrew's journey through, you guessed it, space and time. We call that line that represents Andrew's journey his world line. If Andrew jogged instead of walking, he might be able to get past a fence post every second. Well, he's not very athletic. Anyway, when we look at this new flip book from the edge, we can do the same analysis as before. The world line for Andrew jogging is more tilted over than the world line for Andrew walking. We can tell he's going twice fast as before without flipping the panels. But here's the clever bit. In physics, it's always good to view things from others' perspectives. After all, the laws of physics should be same for everyone, or no one will obey them. So let's rethink our cartoon and have the camera follow Andrew jogging along as the fence posts approach and pass behind him, still viewing it as a flipbook of panels. We don't need to redraw anything. We simply move all the cutout frames slightly until Andrew's tilted world line becomes completely vertical. Yes, now Andrew is stationary, just jogging on the spot in the center of the panel. On the edge of the flipbook, Andrew's world line was going straight upwards. The fence posts are coming past Andrew. It's now their world lines that are tilted. This rearrangement of panel is known as Galilean transformation. and it lets us analyze physics from someone else's perspective. In this case, Andrew's. After all, it is always good to see things from other point of view, especially when the viewers are moving at different speeds. So long as the speeds aren't too high. If you're a cosmic ray moving at the speed of light, our flipbook of your point of view falls apart. To stop that from happening, we'll have to glue panels together instead of a stack of separate panels. We'll need a solid block of space-time. Let's reintroduce second cartoon character, Tom. Now consider Andrew project laser light on Tom. Light. It's the fastest thing in the universe, but we can still measure its speed. If we slow down the animation, we can analyze light's motion using a space-time diagram, which takes a flipbook of animation panels and turns them on their side. In this video, I'll add this single experimental fact that whenever anyone measures just how fast light moves, they get the same answer: 299, 792 and 458 meters every second. Which means that when we draw light on our space-time diagram, its word line always has to appear at the same angle. But we saw previously that speed or equability word line angles change when we look at things from other people's perspective. To explore this contradiction, let's see what happens if Tom starts moving while Andrew stands still and shines the laser at Tom. First, we need to construct the space-time diagram. Yes, that means taking all of the different panels showing the different movement in time and stacking them up. From this side, we can see the whole line of the laser light at its correct fixed angle, just as before. So far, so good. But that space-time diagram represents Andrew's perspective. What does it look like to Tom? We showed how to get Tom's perspective moving all the panels along a bit until his whole line is completely vertical. But look carefully at the light's whole line. The rearrangement of the panels means it's now tilted over too far. Tom measured light traveling faster than Andrew would. But every experiment we've ever done, and we've tried very hard, says that everyone measures light to have a fixed speed. So let's start again. In the 1900s, a clever chap named Albert Einstein worked out how to see things properly from Tom's point of view, while still getting the speed of light right. First, we need to glue together the separate panels into one solid block. This gives us our space-time turning, or one smooth continuous material. And now, here is the trick. What you do is stretch your block of space-time along the light whole line, then squash it by the same amount, but at right angles to the light whole line, and abracadabra. Tom's whole line has gone vertically, so this does represent the world from his point of view. But most importantly, the light's whole line has never changed its angle. And so, light will be measured by Tom going at the correct speed. This is a super trick known as a Lorentz transformation. Yet, more than a trick, slice up the space-time into new panels and you have the physically correct animation. Tom is stationary in the car. Everything else is coming past Tom at the speed of light. Work out to be that same fixed value that we know everyone measures. On the other hand, something strange had happened. The fence posts aren't space a meter apart anymore, and Andrew looked a bit thin. But that's not fair. Why don't Tom get to look thin? As physics was supposed to be the same for everyone. Yes, physics is same for everyone. All that stretching and squashing of space-time has just muddled together what we used to think of separately as space and time. This particular squashing effect is known as Lorentz contraction. To see world with respect to Andrew, we should redraw, and the scene look like to Andrew. To Andrew, Tom appears Lorentz contracted. Just as the space gets muddled with time, time also gets muddled with space, and an effect known as time dilation. No, at everyday speeds, such as Tom's car reaches, actually all the effects are much smaller than we've illustrated them. Oh yet, careful experiment, for instance, watching the behavior of tiny particle whizzing around the Large Hadron Collider confirm that the effects are real. And now that space-time is experimentally confirmed part of reality, we can get a bit more ambitious. What if we was to start playing with the material of space-time itself? Gravity. It controls the universe. Everything attracts everything else. We explore what gravity means for space-time, or rather, what space-time means for gravity. Until now, we've been dealing with things moving at constant speed, but straight world lines in space-time. But once you add gravity, if you measure a speed at one moment, then again a bit later, the speed may have changed. In other words, as I discovered, gravity causes acceleration. So we need the world line to look different from one moment to next. As we saw, the correct way to tilt an object's world line is using a Lorentz transformation, Einstein's stretch and squash trick. So to map out what gravity is doing to Tom's motion, we need to create a whole load of little patches on space-time, each transformed by different amount, so that my world line is at a different angle in each one. And then we're ready to stitch everything together. We assemble a cozy quilt of space-time where world lines look curved. Where the world lines join, the objects collide. By making these connections between the patches, a curvature gets built into the space-time itself. But Einstein's true genius was to describe precisely how each patch is stretched and squashed according to nearby mass and energy. The mere presence of stuff curves the space-time, and curving space-time moves the stuff around. This is gravity, according to Einstein. Previously, Isaac Newton has explained gravity using the ideas of force and acceleration without any wibbly-wobbly space-time, and that did pretty well. But Einstein's theory does just slightly better at predicting, for example, the orbit of Mercury around the Sun, or the way that light rays are reflected by massive objects. More importantly, Einstein's theory predicts things that simply don't exist in older theories where space, time and gravity are separate. This stitching can leave wrinkles in the space-time material. These are called gravitational waves, which should be detectable as tiny, repetitive, subtle squashes and stretches in space. So we are building experiments to check if they are there. In the meantime, indirect evidence, most recently in the polarization patterns of light left over from the Big Bang, strongly suggests that there are But despite Einstein's successes, when too much stuff gets contracted into a small space, like in a black hole, the curvature of space-time becomes so large that his equations collapse. We need a new picture of space-time that incorporates quantum mechanics to unlock the secret at the heart of the black holes, which means there are plenty more to be discovered about space-time and space-time in the future. Thank you so much for giving me the opportunity. Thank you.